Okay, so today we're going to be talking about problem 13 in chapter 7. And even though this problem may seem like a lot of words that you might not know, don't get bogged down by terminology you don't know. This is a very straightforward problem that's really kind of simple to do. So the problem asks you essentially to find the frequency and wavelength of this gamma ray. So we're gonna break this up into two parts. The first part we're gonna try to find the frequency, and the second part we're gonna try to find the wavelength. So the first thing you want to do in every single problem you have is to write down what they give you in the problem. So they tell you that the gamma ray has an energy of 1.33 mega EVs, which is a million electron volts. You're going to write that down. So your known is 1.33 mega EVs. So what you're going to want to do with this type of unit here is essentially convert it to joules, because if you remember in most of your lectures and texts, most of the energy is in joules. So you're going to convert that. So what you're going to do is going to start converting. So 1.33 mega EVs, which is just a million electron volts, as they say in the question. You're going to just do a simple unit conversion. And then you want to somehow get to joules. And they give you essentially the conversion to joules in the problem. The conversion to joules in the problem. So 1 EV equals 1.602 multiplied by 10 to negative 19 joules. Right? So once you convert all that out, you get 2.13 multiplied by 10 to the negative 13 joules. So you're gonna use this energy unit throughout, that energy number throughout. So what we're gonna do now is try to find the frequency to this problem. So in your lecture and in the textbook, they give you a simple energy equation. Delta E, which is the energy, I'll write down energy here, or change in energy actually, because the delta really means change, equals H, which is Planck's constant, which I think is something you have to memorize for your test, multiplied by nu. And nu is essentially the frequency, and it kind of looks like a V, but don't confuse the two. A nu kind of has, a V kind of looks like this, and a nu kind of has a nick in the lettering. So just remember that a nu is frequency. So what you're going to do is you want to isolate your frequency here. So write out the equation again, and you have something like this. So to isolate your nu, you're going to divide each side by Planck's constant. So you get nu equals delta E divided by H, or Planck's constant. So now from here, it's just a regular plug and chug. So you take your energy value, which you found in your conversion, and you divide by Planck's constant. So you do 2.13 multiplied by 10 to the negative 13 joules, divided by Planck's constant, which it's memorized, is 6.626 multiplied by 10 to the negative 34, sorry, I wrote a J there, 34 joules second. And what you want to do in every single problem when you get an answer is to check the units. And you know that frequency will be given in either hertz or essentially inverse seconds. So if you cancel these units, you see that you have an inverse second here, so you know you're on the right track. So when you essentially calculate this out, you get a number that's 3.2156 multiplied by 10 to the 20 inverse seconds, which can just be simplified to 3.22 multiplied by 10 to the 20 hertz. So this right here is your answer, and let me see if I can write that. I'll write it onto the side so that when I erase it, it'll still be here. So let's see, this answer would be well, yeah, this answer would be 3.22 multiplied by 10 to 20 hertz. So that's just on the side so you can see it for later. Let me erase this so we can do the second part. So now the second part is asking you about is trying to find the wavelength. And the equation they give you in your lecture and in your textbook is something like delta E equals hc over lambda. And so your delta E is essentially the same thing as change in energy, and your h is just Planck's constant again. Sorry. And your c is just the speed of light. And this symbol here, which is that's a symbol for wavelength, it's called a lambda. So this is going to be wavelength. And essentially, this equation comes from the original equation you worked with in the last part. It essentially comes from here because your frequency is essentially nu equals c over lambda. So that's kind of how you get to this equation. If you ever forget, if you memorize these two equations, you can definitely get to this equation. So that's just for your own information. It's usually good to know. Okay, so now what you want to do is you want to find the wavelength, right? So you're going to try to isolate this wavelength here. So you're going to multiply each side by lambda so that you have the delta E equals lambda equals hc. So to isolate your lambda, what you're going to want to do is divide each side by delta E. So that now you get lambda equals hc divided by delta E. So now all it is just a basic plug and chug. So you do your Planck's constant, 6.626, multiplied by 10 to the negative 34 joules second, multiplied by the speed of light, which is 3.0, multiplied by 10 to the 8th meters per second, divided by the energy, which you found over here in your, which is the first thing we did. So 2.13 multiplied by 10 to the negative 13 joules. And I'm going to erase this equation here so we can write our answer. So hopefully you have that copied down. So then your answer for part 2 would then be approximately 9.33 multiplied by 10 to the negative 13 meters. And that makes sense because it's essentially trying to find the wavelength to an atom, which an atom is extremely small.